Welcome to SciRM Triple E YouTube channel. Let us solve some problems based on power systems stability analysis. Comes under power angle equation, right? So example number 2. So power angle equation during the fault. Okay. So we'll determine now the required datas. So this is one diagram, single line diagram. Otherwise, you can consider one diagram of power system analysis. There is a 3 buses are present, 1 2 3. See here also one bus will be there, just to consider ABC. Okay, so bus 1, bus 2, bus 2 here, bus 3 here. So otherwise you can take this one as a reference bus. Okay, so convert the read line which is in Y form, okay, admittance form, into delta. Remove the node 3 from the network, right? See here I have given some basics over here. If you want to convert delta to star or star to delta, so which formula will prefer? So just you go back one third semester, okay, till third semester. So there we studied in the electrical circuit analysis, star to delta conversion, delta to star conversion, right? So delta to star we have to use this formula. See here, if you want to calculate RA, I'll just draw like this. Here resistance, okay, here on resistance, here on resistance. It looks like a star. So if you want to calculate RA, this is RA I'll take, okay. RA is equal to what? This into this divided by total, right? So if you want to calculate, I'll just draw here delta, okay. And if you want, this one is RAC, this one is RAB, and this one is RBC, and this one is RAC, right? If you want to calculate this part, right, this part, see here, RA plus RB plus RA into RB divided by this RC. See here, if you take RA common outside or RA this side, so what you will get? RA plus RC, RA plus RC divided by RA RC divided by RB, right? This formula, right? So based on that we have a data over here. They have given values of here to here and then here to here, and 3 to 2 and 1 to 3 and 3 to B. Just you substitute if you want to calculate RAC. See here, RAC, it looks like a star, okay, but we need to convert it into delta. So RAC you calculate, RAB you calculate, RBC you calculate, you'll get these values, right? So but just to concentrate on star to delta conversion and delta to star conversion, just to remember these formulas, right? So next we'll move on to the next question. Approach 2, same question, approach 2. Convert the red line which is Y form into delta, remove the node 3 from the circuit diagram. See here, if this one is looks like a star, right, and it is converted into delta. See, complete this one will be there. So this is a star, okay, 3 star. This one is delta, complete loop will be there. So if you want to calculate P max is equal to what? E1 E2 dash Y12, right? Where y1 is equal to what? Minus 1 by j 0.13. This one is 1 to 2, right? So 1 to 2 node. So y1 is equal to minus 1 by j 1.3. You'll get 0.769. So P max is equal to what? 1.05, 1, this one e2 dash, and 0.769 is a y12. Finally get this answer, right? This is the overall solution for this problem. So next we'll see after the fault on problem, okay. So the fault in the system cleared by simultaneously opening of circuit breakers at each end of the affected line, determine the power angle equation and the swing equation of the first fault period. See here fault dimension, definitely circuit breaker will be involving here, and if switching devices are here very much important, like relays and circuit breaker coils and then the current CTs, because CT only measure high current and then send the signal to circuit breaker. How we will get to know fault is occurred in the power system components or any appliances or any electrical components. If suppose current reaches this limit, then only we'll come to know there is a fault, right? So here there is a pre-fault condition on diagram they have given. We have to analyze this diagram and we have to solve the problem, right? Here they mentioned infinity over here, right? uh, Next we'll solve problem that in previous slide. So y1 if you want to calculate, that is 1 by j 0.2 j 0.1. So finally we will get minus j 1.249. If you want to calculate this one, p is equal to pm into sin delta, y12 is equal to j 1.429. Just to calculate 1.5 sin delta. So this one is a single equation. So h by pi f, pi is 180 and f is here, and d square delta by dt square, you will get this value is a final one, right? Synchronizing efficiency, synchronizing power coefficient. See here, this one is a uh, coefficient of power, right? So power from the power angle curve, two values of angle satisfied. One is power, another one is degree angle, right? So from this, this one is during fault, this one is before fault, okay, before this red line, and then after this one 1.5 sin delta, and then during fault this one, okay, this green line. So 28.44 degree acceptable operating the point. Acceptable operating point is that the synchronism in small temporary changes occur in the electrical power output. So if suppose synchronism occurs, small variation occurs, small fault occurs, that will manage, I mean it will make a stable operation. So it will not shut down like power system whole components. See, for example, I'll tell you, if suppose of while inserting the plug into the socket, sometimes you will get a shock, right? I mean, not shock, you will get a spark, right? Spark in the sense like lightning will occur in small one. So it will not harm for the electrical appliances, I mean sometimes, okay, and even the person who is operating. So I mean, it will make a stable operation. So if suppose the current reaches beyond the limit, then only the power system MCB will trip off, or electrical fuse wire will get melt out. So that's based on this one. I mean, one limit will be there, one standard value will be there. So it reaches the limit, then only it will affect to the power system components. The overall concept, right? So let's see next video, like equal area criteria and um, some problems also we will solve. Let's go on to the next video.